Welcome back, guys. In this session, we are going to finish the revenue structure for case 5, the RA plus arbitrage case. In the last lesson, we modeled the resource adequacy revenue. In this one, we will layer the merchant arbitrage on top so that the green merchant arbitrage bar in the revenue chart is fully driven by the model. If you're new to this Deal Lab series, I recommend starting with part 1, where you can download the start file for free and build the model alongside me. Link is in the video description below. Let's jump back to the monetization pillar 1. We are still in the middle column here, the RA plus arbitrage for our BESS structure, but this time we are focusing on a merchant overlay. The key new parameter for us is the equivalent full cycles for arbitrage, 120 per year. That's relatively low, and that's deliberate. The battery is first and foremost committed to the resource adequacy product, so we only have limited headroom to monetize price spreads. For the debt case, the merchant cash flows are also haircut by 20%, so for debt sizing purposes, lenders only give partial credit to merchant arbitrage assumptions. And finally, note that the arbitrage is based on a 4-hour RA constrained price curve. In other words, this is not a fully free merchant battery. We can't always charge at the absolute daily minimum and discharge at the absolute peak. Switching over to the inputs time independent sheet for case 5. You can see the same story reflected here in the merchant energy arbitrage block. Start is at COD and the arbitrage term is 20 years, matching the resource adequacy contract term. The merchant price case selection in row 119 is set to 4-hour BESS RA constraint. That tells the model to use the constrained price curves rather than the pure merchant 1-hour or 2-hour cases that we will use later for other scenarios. Below that, we specify the arbitrage capacity, the cycles per year, here 120, and the share of installed capacity that is actually used for arbitrage. Now let's quickly hop into inputs time dependent. Down here in the revenue related forecast section, you can see the merchant arbitrage charge and discharge prices by year. For the live case, rows 69 and 70 pull in the average charge and discharge prices depending on the dropdown we just looked at in the inputs time independent sheet. In practice, these price forecasts would typically come from an independent market consultant. So this part of the model is really acting as a container for their price forecasts. Before we start with the hands-on modeling part, just a quick visual to connect the dots. This dark curve from the Energy Systems Fundamentals course shows how net load and spot prices move over a typical day. A battery charges when the system is oversupplied and prices are low, and discharges when the system is tight and prices spike, usually 1 or 2 cycles per day. In our resource adequacy and arbitrage case, that behavior is heavily constrained by the resource adequacy obligation, which is why we only allow 120 equivalent full cycles per year instead of 365 plus. If you want a deeper explanation of how these price shapes are formed and how storage flattens them, I would encourage you to go back to the Energy System Fundamentals module. Alright, now let's go back into the operations sheet and build the merchant energy arbitrage section together. As always, we will start with our merchant energy arbitrage flag. And to do this as efficiently as possible, we will just pick up the flag from our previous lesson, hit Ctrl C here, and Ctrl V here, F2 to check our references. And the only thing we'll have to adjust is our on-off switch. So we drag this reference here up to cell G177, hit enter and drag this one over, Ctrl R. And unlike for the previous lessons, in this lesson we will actually have to pull in multiple time series price forecasts. And we will start doing this with our merchant charge price, which is the average charge price on a real basis. This row is essentially the price we pay to buy energy from the grid to charge the battery. And what we will utilize here is an XLOOKUP function. So let's type XLOOKUP. And we will look up our year, which is in row 4. Hit F4 1, 2 times to anchor it to the row, comma, and then we need our lookup array, which is in our inputs time dependent sheet. And right here, we will pick up row 69 and 70, which means the years that we're referring to are in row 68. So pick up L68 to AT68, hit F4 once. So that's the lookup value for the year, comma, and our return value, since we now look at charge prices, is row 69. Make sure that you also again go from column L to column AT. And this time we hit F4 1, 2, 3 times to only anchor to the column. And then comma, if not found, we want a 0 to be returned, and the match mode should be exact. So another 0, close parentheses, hit enter. And in addition to the lookup, we will also multiply this by our flag. So let's multiply this with our flag in row 173. Hit F4 1, 2 times. And let's drag this one over, Control R. Let's see if that worked. And you can see for 2030, we, for instance, pull in 29.6 USD per megawatt hour for our average charge price, which should correspond with the value we have right here. And it does. Right here we have $29.6 per megawatt hour we will have to pay for charging our battery, and then we will want to sell it at roughly $128 per megawatt hour. And the price differential between those two prices is what our arbitrage profit will be. Let's flip back over to the operations sheet and hop into cell K177. And if we got the anchoring right, all we have to do is hit Control D, hit F2, and let's see if the references are right. We're still looking at row 68, and then pick up row 70, which is exactly what we want to pick up. So we can drag this one over to the right, Control R. And you can see that in year 2030, we get the $128 per megawatt hour. So that means we have our prices on a real basis, meaning before any inflation adjustments. Nominal prices will be after applying inflation, and that will be essentially K176, so our real price multiplied by, let's do another X lookup, and the lookup value is going to be our escalation choice here, which is merchant. That's an input from our inputs time independent sheet. Hit F4 once, comma, and then we need our lookup array, which is further up in the sheet right here. So let's select all of these 6 cells here, D23 to D28. Hit F4 once to fully anchor that reference, comma, and our return value is going to be this index right here. Hit F4 1, 2 times to only anchor it to the row, comma 0 and comma 0, close parentheses, hit enter. Let's see if that worked. Drag it over, Control R. And you can see that now in 2030, we actually pay $33 per megawatt hour, because we will multiply this by our merchant index of 1.12. Then let's see if we got the anchoring right. Hit Control D right here, hit F2, scroll up, and we got the anchoring right. So we can drag that one over as well, Control R. And now you can see that in year 2030, our spread is actually not roughly $98, but instead $110, because after inflation, that spread widens further, which is good for our overall arbitrage business case. Great, and now that we have determined our prices to charge and discharge the battery, what we will have to do next is determine how much energy we actually need to charge for a full cycle, and then how much energy we can actually supply back to the grid after all our losses and efficiency adjustments. And we will start with our energy needed for a full state of charge window charge. And for this one, we can pick up what we calculated in a previous lesson. So let's scroll up. And in row 63, you can see this is our energy needed for a full state of charge window charge, which, since we now have a 4-hour battery, is over 1000 megawatt hours AC. Because we have quite an overbuild ratio and the initial BESS installed capacity on a megawatt basis is 1050, and for full charge we will need to charge it with 1039 megawatt hours AC, because this number here already considers our usable state of charge window up here. So let's pick up this number, scroll back down, and now we need a few adjustments. And the first one being is our actual capacity that we assume for our merchant arbitrage, which we have here in row 177 and column H. In this case, we assume 100% of the capacity is actually sold as arbitrage as well. So hit F4 once. The actual restricting factor will be our cycles per annum, which is rather low, but our actual capacity we assume at 100%. Although this is going to be constrained through these cycles right here. And then, since we have now only considered our state of charge window so far with the number we are picking up in row 63, what we are missing with this number here is any adjustments for availability and curtailment. So we cannot just disregard availability or curtailment. So we really have to watch out that we are not double counting or accidentally forgetting any of these adjustment factors. So we will continue with an if statement. If our availability adjustment switch here is on, so hit F4 once for this one. If this equals 1, then scroll up. We want our availability adjustment, which is in K32. Hit F4 2 times. And if this switch were to be turned off, so we do not consider any availability adjustment for merchant arbitrage, which would be very unreasonable to do, then we want a 1, so 100%, close parentheses. And then we also have to consider our curtailment factor. So that will be another times if statement. And if this switch here in H184, hit F4 once, equals 1, comma, then open parentheses, and we will type 1 minus our curtailment value that we have further up here. Since the curtailment value is 1%, we want 1 minus the curtailment. So select K33, hit F4 2 times, and close parentheses. And if this switch were to be turned off, so curtailment would actually be paid for within an arbitrage, which is also highly unlikely, then we want 100%. Close parentheses, hit enter. So let's see if that worked, and if you got all the anchoring right, hit Control R. And you can see that after all of our adjustments for availability and curtailment, because obviously if the BESS is not available or curtailed, we cannot monetize any arbitrage opportunity. After all of these adjustments, we would need 998 megawatt hours on an AC basis for the average full cycle charge. And some students might now argue, why do we consider the availability and curtailment adjustment if that is already considered within the cycles per annum? And in our case, our independent engineer or market provider has provided us with cycles per annum that the battery can technically fully utilize using arbitrage before any availability or curtailment considerations, which is why we included this here. But if your forecasts are given differently, you can always turn these switches off. And now let's continue with the next row, which is our usable energy after DC to AC conversion. So this is the energy that we feed back into the grid. So we need 998 megawatt hours on an AC basis to charge the battery. And now we want to figure out how much we can actually sell back to the grid, which will be less than the 998 megawatt hours. So for this, let's pick up this formula, Control C, and paste it special, Alt HVS F for formulas only. Hit F2. And we want to refer to the capacity right here to these two switches. However, this time we do not want to refer to our energy needed for full state of charge, window charge, but instead we're going to drag this one down to row 100, which is our usable energy after DC to AC conversion. So we have already calculated this value right here. Hit enter. And before we drag it over, let's go back to row 100. And what you will notice here is this value here is considering our one-way efficiency, discharge and transformer loss on a discharge basis, and is picking up this value from right here, which is coming from here. And all of these values here do not yet consider any adjustment for availability or curtailment. Only degradation and efficiencies and losses, as well as the usable state of charge window, has been considered so far, which is why here in the merchant arbitrage section, we have to be so careful that we figure out whether this availability and curtailment adjustment is still necessary, which it is. So let's drag this one over, Control R. And now we essentially know that in the first year per cycle, so we're looking here at the average cycle, we need 998 megawatt hours to charge the battery. And we can then discharge 920 megawatt hours after all adjustments. Now this allows us to move on to our charging costs per cycle. So now it's going to get interesting to see how much money we actually make per cycle. And that is equal to our merchant average charge price on a nominal basis. So after inflation, which is in K180, times the energy needed for a full charge, which is in K184. And since we now look at $1,000 US, we also need to divide by 1,000 or 1,000, because this price here is given in USD per megawatt hour. Hit enter, drag it over, Control R. And we see that for a full cycle, we need to pay $30,000 to charge our 200 megawatt AC, 800 megawatt hour nameplate capacity BESS. And now let's do the same for the discharge path. And this is simply going to be our merchant average discharge price on a nominal basis, which is higher than our charge price, times our discharge energy, which is lower than our charge energy. So we do indeed lose some energy here due to round trip efficiency. And again, we divide by 1,000, hit enter, drag it over, Control R. And now you can see that in the first year, we pay $30,000 for charging our battery per cycle, and we'll get paid $117,000, which now allows us to calculate our net profit per cycle in each year. And that is going to be row 187, minus row 186. Drag this one over, Control R. And this is essentially our merchant arbitrage spread in USD terms per full cycle. Now we have figured out our arbitrage per cycle, but what we have not figured out is how much the total BESS per year actually would generate in arbitrage profit. And this is going to be the section down here. So first we will figure out the energy needed for a full state of charge window charge on an entire year. So this is going to be row 184, which is our charge needed per cycle, times our cycles per annum, which is 120 right here, coming from our inputs time independent sheet. Let's fully anchor this one with a 4 times our merchant arbitrage flag. So we want to make sure that we only pick up this energy if the arbitrage is actually on. Hit F4 2 times. And then before we drag it over, let's copy this formula here, Alt-H, VS-F, paste it special here, hit F2, and all references here are right as well. So we can drag this one over, Control R. So now we have the energy needed to charge and discharge for the full arbitrage energy amount we will need per year. And now we can almost calculate our overall merchant arbitrage profit. So first we need to determine our costs. And that is going to be equal to our charging costs per cycle up here. So there are multiple ways of how we can calculate that now, but I'm just going to use the charging costs per cycle in 186. Multiply this with our cycles 120 per year, hit F4 once, and multiply it with the flag up here. You can also calculate it with using this energy amount here and multiplying by the nominal price, but I'm just going to do it this way. It doesn't really matter how we do it. Hit F4 2 times. And for the discharging revenue, it's the same principle. So this is going to equal to our discharging revenue per cycle times our cycles per annum, 120, hit F4 once, times our merchant arbitrage flag. Hit F4 2 times. Enter, drag this one over, Control R. And now we can see that in the first year, we need to pay $3.6 million to charge our battery, and we get paid $14 million. And to calculate our merchant energy arbitrage profit, all we now have to do is take our discharging revenue and subtract our charging costs from that. Hit Enter, drag it over, Control R. And you can see that over a 20-year period, we would make $256 million in merchant arbitrage profit. And we would have to pay $86 million to charge our battery and would get a revenue of $342.8 million for discharging the battery. Okay guys, that completes the merchant energy arbitrage block for case 5. If you're confused about some of the BESS related terms and acronyms, I highly recommend looking into our BESS secret sauce, where we have a lot of valuable explanations for all the different BESS related terms. Together with the resource adequacy revenue from the previous lesson, we now have a fully modeled resource adequacy and arbitrage structure, which is the industry typical BESS structuring approach. And in the next lesson, we will model our auxiliary services contract, which is another fixed price contract. Alright guys, I will see you in the next lesson. See you there.